did a lot of research papers from IISc, so he's really good researcher who has worked both in IISc and IIT. So
And let's not forget, he is an inventor. His research is shaping the future of robotics and technology. Today, we are pleased to invite you to an insightful session on David Heisenberg DH parameters, conducted by V.S. Rajshekhar sir from IIT Kanpur. This session will provide a deep understanding of DH parameters, which are fundamental in robotics kinematics.
so exactly, let's dive right in. Sir, we are pleased to have you with us, and we are eager to learn about this.
Okay, thanks Kritika and Muskin for the introduction. I'll start sharing the screen. I hope you can see the full screen view.
Yeah,
Yeah.
it's
Yes.
visible.
Okay. A very good afternoon to everyone. This is V.S. Rajashekhar. I'm a PhD scholar at the Hive Lab, Harmony Interaction and Versatile Exploration Lab at the Department of Design at Indian Institute of Technology, Kanpur. Uh, for today, we'll be talking about the forward and inverse kinematics of robotic arms. I hope I'm audible.
Yeah, Rajshekhar.
Yes, you're audible.
Okay. Today we'll be talking about the forward and inverse kinematics of robotic arms. We'll be dealing with the math model, coding, and its applications. We'll be starting with their applications so that you will have a understanding of where these robotic arms are being used, and then we will look and dive into the math models, and then we'll convert those math models into codes using Python language, and then we will code using the link which has been posted in the chat box. So, a brief about me: I did my schooling at Ballap Matriculation High Secondary School in Chennai. I did my bachelor's in mechanical engineering at Adiparashakti Engineering College, which is affiliated to Anna University. Masters in advanced manufacturing from Shastra University in Tanjavur, and currently I'm doing my PhD in design from Indian Institute of Technology, Kanpur. In between my masters and doctorate degree, I worked at Indian Institute of Science, that is IIC Bangalore, as a researcher for about 4 years. My area of interest lies in the center of robotics, where I focus on mobile robots, bio-inspired robots, multi-body dynamics, manipulators, aerial grasping, computer-controlled robots, mechanism design, and component robots. These are a few robots which I have made in the past decade. You can see the snake robots on the extreme left. These are the primary focus which I do in the field of robotics. And this is the stack climbing robot which we made at IIT Hyderabad. And this is a robotic arm, simple robotic arm. And these are the robotic lizards which I did in the past. And these are the aerial grippers. This is the aerial gripper with a magnet at the bottom, which can carry load, which is ferrous coated on the using the drones. And this is a gripper kind of mechanism where it carries a spherical object in space. And this is a reconfigurable robo which can be reconfigured into 7 or 8 types of robots. So this is a manipulator, and this is a biped and a quadruped. And these are other small robots which are benchtop models, and these are functional. I also focus on creating GUI for robots, where you can see the GUI over here and the real robot over here, and their performance will be mapped to the graphical world. And most recently, I'm focusing on extended reality using the heads-up displays and soft continuum robots, that is the snake robots. So before going into the session, we'll have a look at a robo which was made by our own defense for what you call, for the defense applications such as finding and disposing bombs. So as you can see, it is a mobile robot with a robotic arm attached on top of it. The robotic arms need not be actually fitted to the ground. It can be made available on the mobile platform also. So if So this is the graphical user interface for the robo, and as we go on, we'll be able to see some visuals where it disposes the explosives. It has a portable X-ray, this is the suspected object which it takes and it scans it, and using a jet of water, it actually breaks it into pieces. So this another is an application where it is being used at Fanuc. Fanuc is a world leader in robotic arms. They are good manufacturers of robotic arms, and this is a plant in Mercedes Audi where you can see the cars being assembled using the robotic arms. This is the engine getting assembled using the robotic arm, and this is the inspection which is being done on the robos. This is spot welding, and this is the inspection which it does for the after the welding. So this another is a robo which I created for educational purposes. This is the CAD model and this is the real robo. So this is the robo which was created using a CAD software called as FreeCAD. So the CAD model was made and it was 3D printed using Ender 3 3D printer, and it has the capacity to do benchtop operations and for learning purposes. As you can see here, it is trying to pierce a balloon, and this was in slow motion. Also, it can carry a very lightweight payloads, and it can maneuver in space. So, when the first question which people ask me is, how do I start learning robotics? So, this is a short video which will guide you through what kind of robots you can make in the beginning. So this is, you can start with a robotic arm, and then you can try to venture into mobile robots such as crawling robots, as you can see over here, and then you can get into legged robots. So the difficulty gets a little bit more, and then you can get into stair climbing robots or wall climbing robots, for which the difficulty is much more, and then into aerial robotics, that is the robots which fly in the air. Okay, coming to the into the topic of robotic arms, what is a industrial robotic arm? Any idea? Anyone can tell, even though the definition is on the screen. What you might have a perception. Does anyone like to tell something? What do you say? What do you feel when the word industrial robotic arm is comes up in front of you? The word industrial robotic arm, what does it mean to you? Any participant? Okay. So I think no one is willing to answer as of now. Uh,
Someone
uh,
hands. Someone raised their hands.
yeah, they can answer. I
Yeah,
cannot.
please speak up. Don't no need to raise hand and all. You can speak up. Okay, Sunil, Sahil, sorry.
So something that is meant to do the same mechanical job time and again.
Okay, very good. Uh, any more definitions from your side? Okay.
I would say yeah, robo capable of doing precise stuff repeatedly, like for cutting, painting, and stuff like that.
Okay, very good. So this, okay, fine. Now we'll get into the definition. This definition is given by the American Robotics Association, which is currently not that active. But when the industrial robotics took a revolution in the US, and they had given this definition, which is reprogrammable, multifunctional manipulator designed to move materials, parts, and tools for specialized devices for various programmed motions to perform a variety of tasks. So the key highlight is variety of tasks, doing variety of tasks using a single robotic arm. It should be, if it is capable of doing painting, welding, pick and place, inspection, and things like that. So that is what is the function of a robotic arm. So coming to the question, what is a manipulation? So manipulation is of two types. One is it consists of gross motion and another is fine motion. In the gross motion, it is for reaching the object. The fine motion is for operating on the object. If both reaching and operation are done, then it is called a manipulation. So it need not be a robotic arms just like this. It can be a parallel robotic arm, robotic manipulator, something like this, which you can see on the screen, extreme bottom right. So this is a parallel manipulator and this is a serial manipulator. We'll come into details very soon. Serial manipulator is something where the motors are connected in series. Here it is in the parallel manipulators, there are motors which are connected parallel to each other with a mechanism which operates the table which is on the top. So that is the difference. So what is a robot made up of? The components of an industrial robot consists of an industrial robotic arm, which consists of a manipulator and a controller. The manipulator consists of a mechanism and actuator, and the controller consists of processor, sensors, and human-machine interface. This is the human-machine interface, which is the controller, and this is the robotic arm, which is the main part of the robot. Applications. I don't want to deal much with applications because you must have been seeing videos on the internet and textbooks you must have studied. Just I kept it short in one slide. This is the use for manufacturing. It can be used for medical applications, the robotic arms. It can be used for military surveillance, a substitute for soldiers and bomb disposals. It can be used for domestic purposes, for assistive purposes at homes. It can be used in agriculture for de-weeding and planting seeds and things like that. It can be used for space exploration to collect samples. It can be used underwater to do inspection on the underwater environments, or ships underwater. The submarines inspections can be done using these kind of robotic arms. Okay, there are two mechanisms as I showed you earlier. This is a serial mechanism and this is a parallel mechanism. Uh, sorry. The the thing is that open loop versus closed loop mechanisms. So I hope that everyone is aware of the two sports. This is cricket and this is table tennis. When you play table tennis, you play with only one hand. The ball, you hit the ball with the bat, and the other hand is just in the air, free, giving contributing to the motion of the bat. But in cricket, you need to hold both the hands together. So only then you can hit the ball with the bat. So the thing which I'm trying to say here is this is open loop. The correction, any correction which has to be made is depends on the only one hand. But if any correction needs to be made in cricket, holding the cricket bat, it is like a closed loop. So this is the loop which is getting closed from the two hands, where you need to adjust both the hands. Only then you will be able to make a difference in the batting style. So this is the how the open loop and the closed loop mechanisms work. Now getting into kinematics of serial mechanisms, in this session we'll be dealing only with the serial mechanisms. This is a serial robotic arm. So here this is the length L1 and the joint angle Q1, and this is the joint, second joint, third joint, fourth joint, and here the rest of the joints are there. And if we know the joint angles, and if we want to calculate the end effector is nothing but the region of interest where the painting or the paint brush or the painting spray or the inspection system is actually kept. So if you are going to keep it over here, this is called as the end effector. So if the joint angles are known, and from that if you calculate the x and y position,
Yeah.
then it is called forward kinematics. Yeah. Someone wanted to tell something? Okay. In inverse kinematics, it's the other way around, where the x, y, and theta are known of the end effector, and then we try to calculate the joint angles, back the joint angles from the information which we get over here. So this is the forward kinematics, and this is the inverse kinematics, knowing the x, y, and theta, and we come to know the joint angles. That is called as inverse kinematics. If anyone has any doubt regarding this, you can feel free to ask, because this is the one which we are going to deal with it both mathematically and in the programs which we are going to do in the rest of the session. If you want me to repeat, you can tell me, I'll repeat it.
Sir, can repeat?
Yeah. So this is a robotic arm where there are joints. The circular portions are the joints, and there is an end effector where the object of interest is there. It can be a gripper where it holds the object. Here, if we know the joint angle, theta 1, that is the Q1, Q2, Q3, and Q4, we can tell what is the position of X, Y, and the theta, that is the end effector. If we know the angle 1, angle and Q2, Q3, and Q4, we can say where the X, Y, and theta is. So if this is called as forward kinematics. So this is where you calculate, we know the joint angles and we get the end effector position, that is forward kinematics. But when it comes to inverse kinematics, we only know the x, y, and theta. These three data we know, and we try to calculate what should be the position of the joints, so that this can take, the robot can take, so that it can reach this position. So that is called as inverse kinematics. So the x, y, and theta are known, and we calculate the inverse kinematics to get the joint angles Q1, Q2, Q3, and Q4. So in inverse kinematics, Q1, Q2, Q3, Q4 are unknown. Only X, Y, and Z, X, Y, and theta are known. Are you able to understand?
Yes, sir.
Yes, sir.
Okay. I hope I can go forward. So this is a simple block diagram understanding. So the theta, whatever values we have, it is called as joint space, and x, y, z, and theta x, theta y, theta z are the Cartesian space. This is for a 6-axis robotic arm. So 6-axis robotic arm means that it can move in the x direction, y direction, and z direction, and it can rotate about the x direction, y direction, and the z direction. So if the theta is known, it is called as, and the x, y, z, theta x, theta y, and theta z are calculated, then it is called as a forward kinematics. Otherwise, if these x, y, and z, and theta x, theta y, theta z are known, and we calculate the inverse kinematics, we get the theta 1 to theta n in space. So, okay. Now going to the closed loop versus open loop mechanisms. So this is a 4-bar mechanism where there are 4 links. 1, 2, O1A is one link, AB is another link, O2B is another link, and O1, O2 is a link. Although they are not connected, they are all on the ground. That's the representation. So in closed loop mechanism, if there's a force acting on AB and that caused the bending, even if the actuator is going to rotate precisely, the error which is happening over here is going to be what you say, it's going to go on forever. But if you take a serial robotic arm, if AB is O1A is a link, AB is another link, and BC is another link, if there is a bend in the link AB, due to the force F, what happens is, since it is open loop, so this AB will rotate a proper to appropriate angle, so that this point C is reached by this point. So this error correction is possible in serial robots, but in this error correction is not possible in closed loop mechanisms, which are used in robots. Now we are getting into the math of the transformations to arrive at the forward kinematics equations. So this is very simple. There's a point in space. This is x direction, y direction, and z direction. This is ax, by. This is the value, how many units it is on the y-axis and how many units it is on the z-axis. This is CZ. So this is represented using a unit vector I, j, and k, and the point in space, this is P, is represented as AXI, BYJ, and CZK. All are added together. So that this is the representation of the point in space. Now, next, a vector in space. So this is the vector in space, bx minus axi plus by minus ayj plus bz minus azk. So this is how you get to know about the vector in space using the 2 points, which is over, with one is over here and the other is over here. Next is the representation of a frame of origin in the frame at the origin of the reference frame. So in robotics, what happens is that the X, Y, and Z is a frame. This is the global frame, just imagine. But the local frame of the robot can be N, O, and A. So this NOA is another frame which needs to be represented as F. That is the frame. Here, if you see for how O is represented, it is represented as the distance on the Y, distance on the X. This is the distance on the X, and this is the distance on the Z. That is how OX, OY, and OZ are done. Similarly, NX, NY, NZ, and AX, AY, AZ. The totally 9 values are obtained from this figure to represent a frame at the origin of a reference frame. Next is a frame relative to a fixed reference frame. So what happens here is the frame has moved. In this, if you see, the frame was attached to the ground frame, but here the frame has moved away by a distance p. That p can in 3D is represented as px, py, and pz, and it is and the scaling factor is 1. So if you want to make a robo which is double the size, you can simply put 2 over here, and the entire robo can be scaled up using this value. To be honest, this is the 4 cross 4 matrix, which is the matrix which we will be dealing about in the entire session from now on. So the thing is that this 3 cross 3 matrix, that is this matrix F matrix, which sits inside this matrix, represents the rotation of the rotation of the frame, and this px, py, and pz represents the distance of the point from in the space from another fixed frame of reference, and O000, which is over here, is the perception. So this will always be 0 in the entire process, and this 1 is the scaling matrix. So this 3 cross 3 matrix and this 3 cross 1 matrix and this 1 cross 3 matrix and 1 cross 1 matrix. There are 4 matrices sitting inside this matrix which contribute to different parameters. So are you all clear with this? Or if you have any doubt, you can ask me.
Sir, can you repeat the fourth row representation?
Yeah, this fourth row 000 is a perspective matrix. So this the same thing is used in computer vision also. If you are using in computer vision, this won't be 0. The image can be skewed up. This image, you can skew up an image. You can you can convert a rectangular image into a pentagonal image. The frame, the shape of the image can be changed. So that happens over the using the perspective matrix. But this perspective matrix, that is 000, is 0 because in robotics there is no change which is happening in the rigid body which the robot is made up of. And this 1 which is at the corner, it is usually 1 in all the cases, but this can be scaled up so that you can actually make a robot which is double the size or triple the size just by changing the value at the bottom. And if you change this value, the other parameters will carry forward this value as you move further. Is it clear?
Okay, thank you, sir.
Yeah.
Sir, one second. So once
Yeah.
again, could you explain what does each column represents? NOAP.
Okay. So NOA. So NOA in this this is a frame. X is X Z and X Y and Z. So this frame mutually perpendicular to each other is the global frame. So you can fix a frame on the globe, and you can set a frame for the robo. This robo can be in NO and A. This is represented by that marker that is called as a frame. So you can either call it a marker or a frame. So in this case, it is called as a frame. So what is that OX is? This you can see it in space, right? This O. So that the distance on the x-axis which it projects on the O projects on the x-axis of the fixed reference frame. That is OX. The OY is the amount of distance it has moved, the unit vector, that is the frame is unit vector. It has moved along the y-axis, and OZ is nothing but how much it has lifted up above the ground along the z-axis. So these three values will give you the perception of where this point of the frame is located. So this is fitted into this so that the frame is now moving forward. In this case, the frame was along the was fitted to the origin, but in this case, the frame has moved away because there is a displacement, and that displacement is nothing but px, py, and pz. So that is why we are adding a fourth column to represent that matrix. And since it is a square matrix, we can use it comfortably for computation purposes, which we'll be doing in the further analysis. Is it okay?
Yes, sir. Thank you.
Any more questions? Okay. So since these matrices are there, one rule of thumb is that this 3 cross 3 matrix, if you find the determinant of them, it will always be 1. Although this will take up values less than 0, not less than 0, sorry, values such as 0.0001, even that makes a difference in this rotation. So that will, if you take the determinant of the entire matrix, it will be 1. So the constraints, the three unit vectors NO and A are mutually perpendicular. Each unit vector representing the direction cosines must be equal to 1. So the n dot O is 0, n dot A is 0, and A dot O is 0. Magnitude of n is 1, magnitude of O is 1, and magnitude of A is 1. So these are the constraints. If these doesn't follow the constraint, then there is some mistake in the calculation which we are doing. Okay, now we will do a pure translation alone. So at this point, NO and A is there. At this point, it has moved a distance d so that the NO and A are moved away. Only the translation happens over here. So what happens here is the rotation matrix doesn't happen. Rotation doesn't happen. So the diagonal columns are 1. So that the entire matrix remains the same. So what happens here is you have to pre-multiply the first matrix. This is the point P, and before that you have to pre-multiply it by the value of this matrix, which is D, and you multiply these two, you get the distance Px plus Dx, Py plus Dy, and Pz plus Dz. You can simply ask, if I add the x comma y comma z of this and x comma y comma z of this, I'll get it. But it is true, you can get it. But in robotics, when you are doing some complex operations where this rotation of this frame also happens, that is, this matrix will also take into consideration. That time, the complexity is taken care by this entire 4 cross 4 matrix. So that is why this matrix is not disturbed anyhow, and only the translation happens. So this is the translation matrix, and we are able to proceed forward. Okay, is it clear?
Yes, sir.
Okay. Next, we'll see pure rotation about an axis. So in this case, what happens is the x-axis NOA. So they are all perpendicular to this, and there's a point in space. So what happens is we are rotating the n about the x-axis. So the A moves after rotation. The A moves angle theta, which means that the O has also rotated an angle theta. So this is clear, right? The P should have moved to a new point. So what happens here? This might look complex. You can take a screenshot of this. This is a pure beauty of maths. That is what I would say. This is a combination of geometry initially, where you can figure out the geometry, and you can convert it into a into algebraic expression, and that is the px is nothing but the pn. The This is L1 minus L2, the py. The distance it has moved is py. That is L1 minus L2. That is the py distance. This is the point distance, and pz. That is this is distance. That is L3 plus L4. So this is converted into the trigonometric equations, and this, if you put px, py, and pz into a matrix, this what happens is this gives a rotation matrix about x-axis. So this you will find it very common in textbooks. Rotation of x of angle theta is nothing but since it is about the x-axis, this is 1, and this is the how you get the cos theta minus sin theta and cos theta. So this is how it is converted into a matrix. So we see something in geometry, we are converting it into algebraic expression. That algebra is converted into matrices, and the matrix is visualization is seen over here. This is little difficult to catch in the first go, how this subtraction and things happen. You can actually, I'll also share this slides with you. You can take a screenshot of it and you can do it in the later stages after the workshop. Okay, so this similarly you can do it for rotation about y and rotation about z, so that you can get the rotation matrices. So that is what I want to say. So what happens when three successive transformations happen? A rotation of 90 degree about z, followed by a translation of 4 comma minus 3 comma 7, followed by a rotation about 90 degree above y. So what happens here is about rotation about y, translation, and the rotation. So these are converted into the matrices and they are multiplied, and we want only the position. So the position of the initial point is given. This is the point, and we convert it into a final position we try to find out. So this is the 8 comma 4 comma minus 1 is the final position. Okay, do you have any doubt on this? Okay. Okay, next is arctan2. Have you all come across this term arctan2 in your huh?
It's a inverse trigonometric function.
It's an inverse trigonometric function. So, but can you tell me the advantage of using arctan2?
Like for example, no matter on where you are, if you rotate about a point, then it will just give you the exact right angle. Like
Yeah.
that. And like for example, if you're in the third quadrant also, and if you want to rotate, it will
Yeah.
not like calculate according to like the along the first quadrant.
Yeah,
I
exactly.
used it once.
Yeah, exactly. So that is the importance of arctan. You should not simply take tan inverse. You should try to take arctan2. That is a function which is in what do you call in Python also, the inverse of the tangent function. But the input which you need to give here is the y and the x. Two inputs you need to give. So what happens here is instead of using tan inverse of x by y by x, you have to use a tan 2 y by x, because it currently determines the angles in all the four quadrants, avoiding ambiguity when x is equal to 0. What happens when x is equal to 0? It goes off to infinity when it is divided. So that is taken care by this. The difference between arctan and arctan2 is as follows. The arctan is the two-quadrant inverse function, but arctan2 is a four-quadrant inverse function. The range is from minus 90 to 90. That is minus 90 is over here to 90. And this is the only range for the arctan. But for the arctan2, it is from minus 180 the whole circle into 2 plus 180. So for an arctan, it takes only single input, but here in arctan2, it takes two inputs. Here it takes array, a numpy array, it takes two numpy arrays as input. So that is the difference between these two. These are commonly used in robotics to find the end effector position. It is used in robot, what do you call it, in a robot motion to find out how what is the position and the direction of the robot motion. And it is used in differential drive robots, pathfinding and obstacle avoidance, sensor fusion and localization, camera and vision systems. So this is the thing. And now coming back to the heart of the topic, DH parameters, that is Genevieve Attenberg parameters. So you can try reading this paper, which was published in 1955. So this is, you can say to some extent, it is outdated, but still for research purposes and lab and hobby projects, we can still use this method. But there are ANN and other computer vision based methods which are being used in the recent days, so that you can compute the forward and inverse kinematics. So here, why to use DH parameters is that the robots have multiple links connected by joints. To control a robot, you need to know the links, how the links move relatively to each other, and how and you need to and this DH parameters provide a consistent framework to define this using 4 parameters per joint. So there are 6 degrees of freedom, but you can just need 4 parameters per joint to determine the position of it. So all the four numbers which we need is rotation about z axis, distance along z axis, length along x axis, and the angle around x axis. So the theta is nothing but the joint angle, d is nothing but the link offset, a is nothing but the link length, and the alpha is the twist angle. So what happens is that so this a joint angle, this distance, this everything forms 4 matrices. So when this DH 4 matrices are multiplied together, this transformation is rotated. Matrix that we arrive as this matrix. Still, you can see that 0001 remains in the last row. So this rotation about z-axis, translation d along z, translation a along x, and rotation of alpha around x. So this gives this matrix. So what the key components are the rotation terms, translation terms, and the homogeneous coordinates. So for an example, we'll take a simple DH element where the where we get only one row of elements, just for a one link robotic arm. So you just give theta as 45, D is 10, A is 5, and alpha is 90. We get this values we get in the substitute, and this is the matrix which gives the final transformation of the robo. It is a single link robo, just a joint in the thing. It's like a analog watch, a hand of analog watch, something like that. So next is a two-link robotic arm, which I will show you the demo. So this rotates about the angle of rotation is given over here, and the offset of the links, length of the links, and the twist angles are also given. We will be dealing with this in the program. And here, if you see, there's a 6-axis robotic arm where you can see the alpha pi by 2, that is, it has rotated pi by 2, and L1 is over here, and it has next thing, it has rotated by pi, pi by 2, and you can go actually substitute this inside this. So this is same over here. And last, if you see the L6, so only the displacement happens, so only L6 is there, displacement has happened. So this table and this diagram will help you in identifying the rotation, the 4 values for the DH parameters. Okay, but before that, we will have a look at the how to calculate the inverse kinematics. I hope you are able to see the screen.
Yeah, it's visible.
Okay, so this is a general solution. So A1, A2, A3, A4, A5, A6 are the transformation matrices of each link. So this, what happens is you multiply all these together, you get a matrix like this. This is just for a visual representation. C1 means cos theta 1, C2, 3, 4 means cos of theta 2 plus theta 3 plus theta 4, and so on. So what we do here is we just pre-multiply it by A1, and we try to find out what happens. So in this case, what happens is we try to take an element out of it, which means that here 3 comma 4, third row, fourth element. So this portion of it is taken out, and we try to calculate. This is not tan inverse really. This should be tan arctan 2, but here it just means the same. So theta 1 we will be able to get. That is, it can be of two values. Zero. Theta can be theta 1 plus 180 also. It can be 180 degree other side also. So from the elements of the matrix which is on the right side, so this side is nothing but RTH is nothing but this matrix. So we'll compare the two matrices, and we just try to find out elements which are favorable to us, and we will try to find out that next thing is theta 3. So this is done by arranging the equations, these two equations, these two elements, we form two equations. These two expressions we square and add them to get an expression. And from this expression, we get the theta 3 from over here. And similarly, if you look at it, the theta 5, the transformation fifth link and sixth link is on the other side, but 4, 3, 2, 1 are on the other side of the or on the left side, and a comparison is made from which we can get the theta 2 and theta 4. So because theta 2 is known, we can get the theta 4. And similarly for theta 5, we can get it by doing the elements 1 comma 3 and 3 comma 2. Two equations are there. We can solve them and we can get it. And finally, theta 6. This can be done by modifying the equations accordingly over here, which you can see on the screen, 2.77, and you can get the theta 6. So this kind of thing is little tricky, but you need to observe which equations can be taken and which can be solved, and so that we can get the required thing from out of this thing. But nowadays, since we have AI and other stuffs doing helping us out, we can ask the AI to do the what do you call AI to do the math for you. Okay. Any doubts so far? Okay. Hello.
Yeah, you're audible.
Okay. So now we'll get into the programming. We'll see a single link manipulator configuration. So this is a link which is at the origin where the joint is at the origin and the link is over here. So this you can open the code where there is 1 hour single solution. I can wait for you to open the code.
We have shared a drive link. You can just open the zip file from there.
This code is pretty straightforward. For forward kinematics, you just need to know the x and the y. That is L so cos theta and L sin theta. And for inverse kinematics, you just give the three values inside x, y, and length of the link. And we can actually take a square root of x square plus y square, and we can find the arctan value of that. And this section of the code is for plotting it on the screen. This R value is used to find out whether the point is outside the reachable workspace of the manipulator. I'll run this. So it is over here. So this is the angle which it is showing currently. So this is 190 degree we have shown here. I have given the input, so it is about 190 degree over here. We'll try changing it to 45. So it changes to 45 degree. So this is for the single solution, and for multiple solution, so it can be either this. So there are it could be either 100 degrees or 460 degrees. So this is the multiple solutions which we get. So this is plotted one on top of each other. Okay. Next we will see how 2R manipulator is done. 2R is nothing but two revolute joint. So one revolute joint over here and one revolute joint over here, and this is a single solution. So we just taken a single solution, but actually if you see, this is a 2R manipulator. When you build something like this is something which I built during my masters. So here is a servo motor and here is a servo motor which writes the letter A on the sheet with the pencil fitted on that end using that pencil. So what happens here is a question for you. There are two solutions. It can either to reach this point. It can either go like this. It can either go like that. So which solution to choose? And that confusion happens where? Where does the confusion happen? Which solution to choose? Any idea?
Can you repeat, sir?
Actually, this robo is there, na? This two links. It is like this. This is the fixer to the ground. This rotates over here. There's a motor over here. This is fixed to this. So this is the end. This is the origin of this. Whatever I showed before. This blue color is one solution, and the orange color is another solution. Because this point to reach this point, you can either reach using the blue solution or using the orange solution. So, can you tell me a situation where the confusion happens? This confusion will happen to the system, whichever you build, if you're giving the equations of motion to it, rather than hard coding it with the angles. If you ask the system to take a thing, where this kind of situation will arise, will create a confusion. Can you tell me a situation where this confusion will happen? Any guesses? So this point can be reached through two ways. One using the solution one, which is in blue color, or using the solution two, which is in orange color. So this point can be reached. So which solution to pick up, that kind of confusion arises, and at the end we will choose only one solution, solution one or solution two. So which can you tell me a scenario where you can choose only one solution out of these two?
I think it depends on the next movement of the robo. If we have to move right, then I have to take first solution or second solution, or if we have to move left, then we have to opt for another solution.
Okay, good. You're close, almost close. That is a good answer. Any more? Just go beyond the math and motion. I can give you a clue. So think of computer vision or object obstacles perspective.
Sir,
Yeah.
so like when we train a robot to crawl, so sir,
Okay.
in that we would only need to fix to one solution.
Okay.
Like it cannot go to the other way.
Okay. Okay. That is in mobile robots, but this is in fixed robotic arms. Here, can you try to apply the same thing? It is possible. Just try. Okay, I'll tell you a situation. For example, this is just imagine this entire square to be a table, and you want to reach this position to pick up a candle or a box which is in this area. But there is a teacup in this region. There's a teacup. There's a cup of tea over this region. So you cannot take this solution. At that time, you need to go for this solution. Only then you can pick up the candle or the object which is over here. So this is how this solution is avoided. This is of no use at that time. You can take this solution route and you can take the uh, object of interest which matters to us. So now we will see that in the code. So here, if you see, there are two solutions and it takes the solution like this. Okay, next we'll see, we'll try to give one as 0 and the other as 0. Can you guess what will happen? The two angles are 0 now. How will the two solutions be? Hello?
Hello. Yeah.
Can you guess how the two solutions be? Before I can show you this.
A straight line.
Yeah, that is what I also believe. Okay, yeah, it's a straight line. Because everything is in 0 degrees. So both the solutions are the same in this case. Okay.
Excuse me.
Yeah.
So what if both the paths or solutions has an object, or if both neither has no objects?
If both the thing has objects, then you need to go beyond the system to take a decision. You can say that robo may be a subsystem. It can tell the master that I'm not able to do it. So that a decision has to be taken. It cannot be solved, or some that kind of the conclusion it should come. If both the solutions are possible, when you think from power consumption point of view, which will consume less power, that is the thing which people usually take into consideration. So which route will take consume less power, and that route will be taken.
Okay, sir. Thank you.
Uh, so now 45, any guesses?
Sir, straight line directly to the point.
Exactly. No, it is not a straight line. So 45 degrees for this and 45 degrees for this. So that has moved 45 degree about this angle. So it is somewhere in between 45 and 90. Are you able to get it? This is 45 degree for this axis,
Yes,
but
sir.
for the second thing, it has moved 45 degree about this axis. So it forms a parallelogram. So if it was 45 and it was 0, theta 2 was 0, probably whatever you said would have happened.
Yes, sir.
No solution. Yeah, it has gone. It didn't create it. It has become infinite. Okay, something like this. Okay, now we'll move into the last part. This is a 6-axis serial manipulator where there are 6 links in space, and this is the representation using cylinders. We have the code along with us. Now we'll try to execute this code and see. And there are 6 joint angles. So I will briefly explain you the code for the for this one with the grouper. So if you can see here, the whatever matrix I showed you is over here, the DH parameter transformation matrix. And for the 6 links, the DH 4 values are given over here on each link about for the each parameter. And the joint angle is initially set to be 0, all the 6 joint angles. And for the forward kinematics, there's a loop which sends the value to the transform DH transform, which is over here. And the DH parameters are taken from that, from the DH table. And there's a cube which is at the end effector, and this is the visualization where the entire code is visualized and it is plotted. So now we will try to run this and show you. Okay, so if you see, this is the base. So this is the base. This is the first link. This is the second link. This is the third link. You can see the red box rotating. Fourth link. And the fifth link. So you can try running this code on your own. And almost at the end of the thing. So today we saw about how the robotic arms how work. I talked about the applications in the industry and how the learning curve happens. The forward and inverse kinematics of robotic arms were introduced, and the exercises were done in the Python programming. And these are the 3 other books which I have written on computer controlled robots and build your own TV remote controlled robots from scratch and voice controlled robots. And here's a QR code to my LinkedIn profile. And that's it from my side. If you have any questions, you can ask me. I'll be happy to answer.
Sir, why we need different axis robots, 3 axis, 4 axis, 5 axis, 6 axis? What are the different functionalities and different operations they perform?
Okay. So the number of degrees of freedom varies because the number of actuators in the robo vary. For example, you need a 6-axis robo to perform all the actions that the human does. For instance, in this robo, this is the hip of the person. It is equivalent to a hip of a person. This is equivalent to a shoulder of a person. This is equivalent to the arm of the person. And this is equal to the finger of the person. So this was inspired from human nature. So that is why the 6-axis robo was involved, which was initially capable of doing whatever human was trying to do. And if you look into the four-axis robo, that is, it has only four links. We are just trying to make the controller simple so that it can, but it can still do the work, taking into consideration it has a mobile base, like something like this on the floor or something like that, and it can perform the action with the help of the motors which it already has. So the lesser the degrees of freedom, the lesser the workspace and the dexterity. More the degrees of freedom, the greater the workspace and the more dexterity it has. So that is what is the use of different kinds of robots, like 4-axis, 5-axis, 6-axis, and things like that.
Thank you.
So,
Yeah,
so like in the two solution method you showed us, a robot can take two paths.
yeah,
But like in the six joint robot, so there can be many parts. So,
yeah.
so how is it decided to take the path?
Okay, good question. So in six-axis robot, there are 8 solutions actually, to be more specific. So it can take 8 parts. 8 solutions are available. So what happens in industrial robots is that the people have a handheld device. So I can show you that. So this is the industrial robo. They have a robo controller. In this robo controller, they try to move the joints so that it goes to a particular location, and then they fix they save that particular dot in the device, and the controller knows that it has to take that joint angles only to move to that point. So it is manually controlled. But in autonomous mode, the robo tries to find out the shortest path which it can take, and it tries to go to the go to the path or the joint angles which are closer to it, and it will try to take that path. So that is how it is done, using the shortest path or the energy consumption. These two things are taken into consideration, and this six-axis robo works in that way, using the 8 solutions it has.
So, so why is it that it is manually coded? Like it can be fitted with sensors to see the obstructions and
Yeah,
accordingly manage to take the path.
yeah, but in industry setting, if you see, the task which is being done doesn't. If you're going for sensors, it is another cost adding to the thing. For instance, if you look at a sealant application, I worked in Tata Automation Limited. We had an application for the Tata Nano car where we had to apply sealant on the base of the car so that the water doesn't come inside. So if we are going to use autonomous robo, autonomous is not required there. We know the particular path it is going to follow because it is coming on a conveyor belt. So at that time, everything is prefixed. For instance, you just try to pick the mobile phone on your table. You will be able to pick it up. Just place it back and just close your eyes and you try to pick the same mobile phone. You will be successful in picking it up in the first attempt. That is because it has memory, your muscle memory. So similarly, the robot will be always having that capability which humans have, so that the sensors number of sensors used should be as minimum as possible, so that the cost of implementation of the robotic system for the entire system, for the entire production line, should be saved. So that is why people don't go for sensors.
Okay, thank you, sir.
Yeah. Any more questions?
So I think no questions are left, right? Hello. Okay, Muskan. Please go on.
Thank you so much, sir, for taking the today's sessions. We are really appreciate to it. Your insights were incredibly helpful, and we are grateful for the opportunity to learn from you. Thank you.
Thank you.
Rajshekar, I will send the photos to you. No worries.
Yeah, okay.
Yeah.
Sir, is this going to be on YouTube or any other platform?
Yeah, I will share the links to the WhatsApp group. Join the WhatsApp group. That's why.
Is this on the robotics one, right?
Session.
There's a WhatsApp group also.
Yeah, we have a WhatsApp group. Just I have pinned this thing. You can just join. Anything you want to just ask, you can ask there. Yeah. I've
It
shared
is
again.
from Saranda club, right?
Yeah, right now it's under Saranda. Yeah. But we have a separate group also for Yantra. Okay, I guess we are done.
Yeah.
Okay, thank you, Rajshekar, for the session.
Yeah, welcome for giving me
Very
an
short notice
opportunity.
to you just came. Yeah, thank you for that.
Yeah, welcome. It was nice interacting with the young minds.
Yeah.
I'm really happy to be here.
Yeah. Thank you.
Yeah.
Thank you.
Okay.
Can we end the meet?